Look closely at this complex automation flow. This is what occurs when a brittle automated process encounters an unexpected data error. The mechanism seizes, halting the flow and paralyzing all downstream operations. Dragging and dropping triggers to create functional logic is an elementary skill. It is the baseline state of low-code development. Most prototypes function perfectly in a pristine testing environment, but a true production environment introduces chaos. External APIs throttle your requests. Networks experience latency. Services go down without warning. When a basic script hits one of those roadblocks, it results in a silent failure. The automation simply stops. The data drops, and the architect receives no notification that the pipeline is broken. This failure reveals the complexity of the underlying systems engineering environment, a reality often obscured by the simple drag-and-drop interface. To transform a fragile script into a resilient enterprise architecture, we apply 7 specific engineering patterns. These 7 patterns operate across 3 distinct operational phases: fault tolerance, compute optimization, and lifecycle management. Integrating these traditional software architecture principles allows low-code systems to run autonomously for months without breaking. The first phase of building resilience requires a basic engineering assumption. All external dependencies and APIs will eventually fail. We manage these inevitable exceptions by applying our first pattern: try, catch, and finally scopes. This flowchart shows a vertical sequence of execution blocks wrapped inside a distinct container. This is the try scope. It houses your main execution logic and risk-prone actions. When an action inside that try scope fails, the system redirects the failure signal downward. It is intercepted by the catch scope, which triggers only on an error payload. At the absolute conclusion, we use the finally scope. It catches pathways from both the try and catch containers, ensuring audit logs are written to your database regardless of outcome. That hierarchy handles internal logic errors, but we also need to mitigate external connection drops. This brings us to pattern 4, retry policies, specifically through the application of exponential backoff. Exponential backoff is a mathematical method where the system waits increasingly longer intervals between retry attempts after encountering a 429 rate limit or a 503 service unavailable error. This mathematical delay allows a temporary network hiccup to resolve itself, preventing it from being registered as a fatal process failure. True fault tolerance ensures the architecture absorbs, logs, and recovers from routine errors without manual intervention. Moving to the second phase, we address the physical limitations of low-code execution. Abstracting the code layer does not eliminate the physical compute costs occurring on the server. Raw data volume and strict API limits are the primary bottlenecks that cause flows to throttle or stop entirely. We protect against this with pattern 3, trigger conditions, deploying them as a strict defensive barrier at the very start of the automation. Default triggers fire indiscriminately on every single database change. That wastes highly limited API calls on irrelevant data. This massive funnel graphic shows 1,200 incoming data points hitting a logic gate. By applying trigger conditions, the gate blocks useless runs, leaving only 40 relevant points successfully passing through. Once the data is inside the flow, we hit internal execution bottlenecks. Apply to each loops are computationally expensive. To optimize them, we use pattern 6, pre-filtering and data shaping, relying on the select action. This diagram illustrates a complex 3-dimensional data tree. Before processing sequentially, we must physically flatten these multi-layered JSON payloads into a lightweight 2-dimensional array that shapes the data. But we also manage the behavioral physics of the loop itself with pattern 7, concurrency control and pagination. By default, low-code loops execute in parallel. When multiple threads attempt simultaneous updates, they cause severe data collisions and record locking in Dataverse environments. The strict architectural rule for concurrency is binary. You must disable it when the sequence of operations matters, and you only enable it when pure speed is required. This data retrieval node demonstrates the absolute necessity of enabling pagination thresholds. It bypasses default limits, fetching sequential blocks to ensure comprehensive data pulls of 350 records. Compute optimization protects the host databases from throttling, while simultaneously improving the automation's overall execution speed. Now we transition from runtime performance to long-term maintenance and organizational scalability. When developers duplicate identical logic, like a standard approval routing, across separate HR, finance, and IT flows, they create compounding technical debt. This animated diagram shows 3 separate flow pathways converging into a single centralized child node. This is pattern 2, child flows. It implements the don't repeat yourself principle in low-code. Centralizing core logic into a single node allows an engineer to patch bugs in one location and automatically inherit that fix across all parent architectures. That efficiency applies directly to the mechanics of application lifecycle management and the physical deployment pipeline moving from development into production. The leading cause of migration failures is the presence of hard-coded infrastructure dependencies, like fixed SharePoint URLs or static database IDs. To solve this, we rely on pattern 5, environment variables and connection references. This is a requirement for cross-environment deployments. This visual shows a logic node migrating across development, testing, and production environments. Environment variables act as dynamic placeholders, allowing the configuration payload to adapt automatically to its new surroundings. Stripping out hard-coded values decouples the logic from the environment, ensuring safe and repeatable application migrations. Strict lifecycle management turns an isolated, unmaintainable script into a governable, scalable enterprise asset. This is a macro view of the fully completed system architecture we have constructed. It combines the fault-tolerant scopes, compute optimization filters, and centralized child flows operating in perfect unison. Compare this complex, resilient, fully documented model with the fragile, linear prototype we examined at the beginning. Low-code syntax changes how we build, but the requirements for systemic quality remain as rigorous as any traditional software environment. Scaling enterprise automation requires actively planning for failure and meticulously optimizing raw compute consumption. The ability to manage technical debt through proper lifecycle variables is the clear dividing line between citizen developers and systems architects. These 7 structural patterns represent the engineering standard for any deployment intended for a production environment. Audit your existing production flows today. Identify any single points of failure that lack these architectural safeguards. Begin your refactoring process by establishing fault tolerance, and then work outward toward compute optimization and lifecycle management. The ultimate goal of low-code engineering is building systems that operate reliably for the long term. The final result of this engineering approach is a business system capable of sustaining operations through high loads and external failures.